Hello everyone, welcome to lecture on formal specification and verification using Coq Proof Assistant. My name is Dr. Vilayat Khan. I'm an assistant professor at ComStats University, Islamabad, WA campus. The topic that I'm going to discuss in this lecture are polymorphism and higher order functions. Polymorphism means to abstracting away the functions where the data they manipulate, or in other words, defining types and functions that are polymorphic. That means that they are accepting any types. They're not dependent on a single type, but they can. The definitions or types are so general that they can be used for any data type. And also higher order functions, which are functions that are taking other functions as the argument. So far we have defined a number of data types and functions and have proved a number of lemmas and theorems where other types, they are all of them are included in the less.v library, which has been compiled and included in this poly.v library. So all of the development related to polymorphism and higher order functions are included in poly.v, and the previous developments are included in less.v, which further include other libraries, basic and induction. So I will continue development of other simple concepts based on polymorphism and higher order functions. So we had defined lists and some functions on list, like repeat and its variants, using polymorphic definition. So I will just compile until the end of our previous development. We had defined a list, which is a polymorphic definition where we have a type variable as the argument, and then we showed that this list can be reused for a list of natural numbers, it can be used for list of bool, and it can be used for list of any other type. So we do not need to define separate a list for natural number and separate list for bool and separate list for any other data type. And the main advantage of this type of definition is that we only need a single definition, and we only need to reuse those constructors. We do not need to invent new names for the new constructors for each type. We can just reuse these constructors, nil and cons and list. And also the functions that are defined for list, for example, repeat, reverse, head, tail, etc. All of these functions can be used for list of nat, list of bool, list of list, and any other types of list. And the most important thing is that all of the developments, called developments like lemmas and theorems, which are proved about showing or satisfying some properties of list, can be reused whenever list of nat or list of bool or list of any type is reasoned about. So this list, definition of list is polymorphic in the sense that it is accepting a type variable, and that type variable can be instantiated with any data type like nat and bool. Then we introduce the concept of implicit arguments, like we have used that kind of implicit argument in the repeat triple prime function, and the implicit argument has the advantage that it is implicit, so we do not need to mention it. The Coq compiler itself can determine the type of the missing variable from this implicit argument. So declaring an argument or parameter as implicit is just by simply including or enclosing it in the curly braces, just like here. We can redefine the same list as above with implicit type variable here. Let me continue with it. Inductive list. I will call this list prime because we are not using this because there is a simple problem with this, and at this stage I would just skip this style of definition. But this is a feature of Coq, so it can be applied anywhere if you like. Okay, so just to teach you that in the list definition, the type variable can be declared as implicit argument. So to declare the type of arguments, the type of values in the constructor can be declared as implicit by enclosing it in the curly braces. So it's a type and it is defined to be as null. Again, the constructor is also named differently than the previous definition of list. So we will be using the previous definition of list, which is polymorphic, and will not be using this definition. But for the time being, just to show an example and naming them differently. Okay, so constructor concatenation cons. It has a value of type x, and it is followed by a list of type list of it's a type list prime. So in the list prime, we are not mentioning the type argument here, the type variable, just like we did here, because we have declared the type argument, the type variable to be implicit. Okay, so let me compile this. Okay, so sorry, cons already exists, so we have to rename it with prime. Okay, so this definition has been accepted. Let me show you an example of how this definition is not very good at this stage. If you are dealing with multiple types, then this type of or this style of definition of inductive definition can be problematic. Let me check. If we check null prime, it has defined where x has a type. So we are not sure about that. If we check null prime net, so it is not accepting because net is a type where this the type variable has been declared as implicit. So we cannot use this. Let me check cons prime, and I'm providing a value 5, for example, and then cons 6 null prime. Let me check this. Sorry, there is a parenthesis missing. Okay, so null prime null prime. Why it is giving an error? Cons prime 5, cons 6 null prime. Type. Okay, let me okay, so let me okay, so list prime is defined and this is accepted. What was the problem with the previous definition? Let me okay, what is the problem with this definition and the one that we have used here? It's exactly the same. And why was this given error? Sorry, we had we didn't have the prime, so that was a typo. Okay, so this is the same definition where x is implicit argument, and when we define list prime, it is accepted, and we can check these constructors where the values are of net data type. So when we compile this, it is accepting this as a type of list prime, so it is okay. It's a list of natural number. And similarly, we can use the same definition where we can define or check a list of Boolean, and it is okay. But if I define here, like here in these check example, the type of values is not mentioned. So we can also include, for example, but it would give an error. For example, in this case, we are making a list of Nate and Boolean, so it would give an error because the first constructor, the cons, is taking 5, so it would consider that cons has been declared as a list of Nate, so it shouldn't accept other values other than natural numbers, so it's giving an error. So in these examples we can see that the type of values is not mentioned here, and it is accepting and it is not returning the type of list which has the values of that type. For example, it is not showing us that it is the list of Nate. Similarly, this check is not showing that it is a list of bool. So it is so general and it can be confusing in some, at least at this stage of our Coq development. So that's why I'm not using this style of definition, inductive definition, where the type variable is implicit. So okay, so but we can continue with implicit types in the function and the functions. Okay, so just like list of Nate, I'm continuing with defining the fn function. Fixed point app is the function for using for fn, and this is a type variable x, which is implicit in this case. So fn function is taking a type variable, and that is implicit, and then it is taking two lists to be appended with each other, and these two lists are lists of type x, and it is returning a list of type x, and this function is defined to be as pattern matching as usual on L1 with. Okay, so what this function is getting, it is getting two lists as the arguments L1 and L2 of some type list of x, and this x should also be provided as the implicit argument. Okay, so when L1 is null, it should return L2, and when L1 is cons ht, like it's a non-null where we have a header and a tail, then it should return as cons h, where h is which h is taken from the first list, and it is concatenated with append continue with the tail and L2. So a recursive call of this append t L2 would take next hit from the tail, and that would be appended after this one, and then until L1, all the elements of L1 are checked. So each iteration would continue with appending an element from the L1, and then at the end it will attach L2. So L1 and L2 would be appended. So okay, let me compile this. So it is accepting. Okay, so let me compute using append. So append, and I'm passing two lists, and let me cons how were we creating examples for cons? So let me take this example here. We already have an example. Okay, so this is the first list, where a list has two elements, 5 and 3, and I'm giving another list, and let me replace this with 5 3, and then 2, and this element is, let's say, 1. Okay, so let me compile this. Okay, so it is giving an error. And why is it so? I think we should not give these types. Okay, the reason is that we have declared the type of cons to be implicit here. So we have defined that this argument, which is the type variable, is implicit, so we do not need to provide the type, and instead it would infer or determine the type of a list from these values. But it is similar to defining the list here, but the difference is that it is now telling us that it is a list of net, while here in these examples for list prime, it was not showing us that it is a list of net and it is a list of bool, while here we have more information about the list of type. So what is the type? So here in this example it is the type net, so it's a list of net. So that's why we are continuing with the previous style of defining inductive types where the type variable is not implicit. It is polymorphic, but it is not implicit. Okay, so append is attaching 5, 3 to 1, 5, 3 to 1, so it is working. We can continue with other definition like defining the reverse function, fixed point, reverse. And again, we are taking the type variable to be implicit, and it is taking a single list of this type, list of x, and it is returning a list of x. And we are using pattern matching on this list. So we have two possibilities. One possibility, the list L can be null, and in that case we should return null. And in the second case, when the list is not null, so cons, it would be of the type head and followed by a tail. And when we come up with this case, we will append. We have already used the function append, and reverse the tail, and will append whatever this reverse tail would return at the end, at the right side of this list. We want to append a list cons h null, a list of only one element, and each time this reverse t is called recursively, this append would append on the right side the element of the element of the list which is taken from the heads. So each iteration takes an element from the head of this list and is appending it at the right side, at the tail, and this way a new list is created. In that new list the elements of the original list are ordered in the opposite order. So that's what we call it, reverse. Let me end this function and compile this function. It is working, and now we can compute reverse, and we can pass a list. Let me call this list, pass this list as argument. Okay, so we should return 3, 5. We have this list as 5, 3. We should return 3, 5. 3, 5. So 3, 5 as a return. So this reverse function is also properly working as this single test indicates. Okay, now we can define a very important function called length to calculate the number of elements in the list. Fixed point, length of the list, and again we are providing the type variable as the implicit parameter, and a parameter L of type list of x, and it returns net. Net means that is the number of that is the number of elements in this list. So it is pattern matching on L as before, and it has two possibilities. The list can be null, and in that case it should return 0, and if it is not null, it is in the form of cons ht, then it should return successor of, and we pass this length function. We call this length function recursively again for the tail, and okay, for the tail, and this function is ended with n dot. Okay, so basically this ends this pattern matching, and this dot ends this definition. Okay, so let me compile this function. Okay, it is okay. At least the compiler accepts this function. And now we can use the compute to find the length of a list. So we, for example, cons 5, cons 3 null, and okay, so the length of this list is 2 because we have 2 elements, and we can change. We can use the same length function. It is independent of the type of the list. So we can, for example, provide a list of bool and can, for example, false. So it is accepting this length function is independent of the type of a list because we have defined it as a polymorphic function. So it is just taking a type variable as the parameter, but this type variable, even that is implicit, so we do not need to explicitly provide that type as shown here in this example. We do not need to provide it explicitly, so it is implicit, and it is it tells the Coq compiler to assign the type, automatically infer the type and assign it to the constructors. So we are not passing the type of the values here, but it is important, it is mandatory, and it is necessary that the list that we are providing must be of a single type. For example, it is a list of bool, it is a list of natural number, and it can be a list of pair. For example, we will see shortly, and that pair maybe internally has more than one type. A pair can be of two different types, so but externally it will be a single type, so it would be acceptable. Okay, so we are defining different functions, polymorphic functions that are not dependent on a single type, but they're general. We can test these functions using some simple example. For example, example test reverse 1, and the example is reverse cons 1 cons 2 null, and when it is reversed, we want to say that this is equivalent to cons 2 cons 1 and null. Okay, so let me compile this. It is working. We can enter into the proof mode. Okay, and we can simplify it. When we simplify it, we get the same result on both sides, and we can close this with auto, and now we can add this with the QED. Okay, so this is a simple test which shows that reverse of this list is equivalent to this list. Okay, sometime we need to tell the Coq that the type of a constructor is, we can tell the Coq explicitly that this is the type of the constructor, and if that type is not required to be passed every time or each time, then we can just explicitly tell the Coq compiler that look, this is the type of the to be used. For example, we can define my null a null, and we want to define a null constructor, and that is defined to be just null. It is giving an error that it cannot infer the implicit parameter x of null whose type is type. I can tell the Coq that please accept this as a false definition, and I'm just showing this so we can use the fail directive, and that would this command has indeed failed with message. The message would be cannot infer the implicit argument x of null, but for the time it has been accepted. But remember that this is a fail definition, that's why it's fail. And we saw that null should have a type argument because Coq cannot infer the type of this argument. But we can define this my null constructor in a different way. And for example, list of Nate, and it is defined to be, it's my null, it has list of Nate, and then it is defined as null. In this case, it's different than the previous definition in the sense that we have defined the type of my null, a new definition. It's a list of Nate, so now null knows that the type of this is Nate, so it can automatically infer the type of this constructor. And sometime we can also define certain constructors or definitions or types, for example my null prime, and it is to be defined as, if you're not giving the type of this constructor here, we can provide the type of the constructor explicitly using the 8 symbol at the rate of symbol. So this is the constructor and I'm providing Nate. So I'm telling the Coq that the type of this constructor is Nate. So this type of constructor Nate is explicitly provided with the help of at the rate of symbol. Similarly, okay, so we can define using other constructors and types with providing the 8 constructor. In the previous libraries, when we defined list of Nate, we had used a number of notations, and we can use similar notations for the list, which is a polymorphic list. So I can continue with notation keyword, and we can reuse those notation x, y, and that is to be defined as cons xy, and the level is it's a precedence level, so we just define this notation to be at level 60, and we assign this right associativity, sorry, it's associativity. So we define this notation to be right associative. So we have just defined whenever we need to use the cons constructor symbol cons xy, then we can use x : y for this constructor. So we would be able to replace in future definition cons h at t with h : t, like that. And similarly, we can use notation for empty list, and this is empty list or null. So we can say that this empty 2 brackets should be used for the null. Let me compile this. Yes. Okay. Similarly, we can use notation for defining a list with elements. So let's we enclose a list in brackets, opening bracket, then an x followed by a semicolon. X represent a value of some type, and then we do this for all many elements, and then it ends with a value of some type, and then it is closed with closing bracket, and this is to be defined as cons x. 2 dots represents it is for any numbers, cons y and it is closed with two empty brackets that represent the null, and then finally two dots again, and then one dot to end this definition. Okay, so there is a type error, and I think that type error is that we have missed a parenthesis, so now it is okay. Similarly, we can use notation for concatenation x plus plus y, and we can continue append x y. So this is concatenation for appending two lists. So this is one list, this is another list, and we are using plus plus for appending, and this is the actual definition that we would use, that the actual interpretation of this symbol should be the definition here that we have already defined. Okay, so we also need to define a level for it, precedence level for it, and that is 60. We just assigned 60. You can assign any other precedence level, and we want this to be right associativity. So if we need it to be left associative, we have to prove it. Okay, so this definition is also accepted, and we can, for example, use these notations. For example, definition list 1, 2, 3. This is a list, and this is to be defined as a list of 1 semicolon 2 semicolon 3, and we can close this with brackets. So this is we have just used definition, the notation, sorry, we have used the notations that we have defined. Okay, so here are some exercises or homeworks for you. Okay, so theorem, append null at the right side for all x of some type. This is a capital uppercase x of some type, for all x of some type, and for all L of type list x. We want to prove that L concatenated with empty on the right side is equal to L. So you have to prove it. So this is very simple. You should be able to do it with try simplification, and if not, then try induction. Okay, so it is homework for you. Let me call it, or let me just write fill in here the software foundation book style, fill in here, and I admit it. I admit this proof, so it is for the time being accepted. Similarly, there is another theorem for you, append associative, and for all A, which is a type, and L, M, N are list of some type A, and then okay, so here we are not using the type because A is automatically inferred to be of type sort TYP, just like we do for other types using the type inference facility of the Coq. So L plus plus M plus plus N. Remember that plus plus means append operation. We say that this is associative, left associative. So L plus plus M plus plus N. Even if we are using the parenthesis here, that is also okay. But if we compile this, they would be automatically, for example, if they would be automatically erased. So these parentheses are not here because by definition, append function is right associative. Append function is right associative. So we have declared this notation to be right associative. So so if there is a parenthesis, this is equivalent to if there is no parenthesis. So there is no need of these two parentheses, so that's why I erase them. So, but these parentheses are important, and we say that if there is a parenthesis on the left side, then it is equivalent to if there are no parentheses. But this is not defined, just like the right associativity here. so we have to free it. And again, this is a homework for you. So prove, and I will say fill in here, and I will again admit this. So admitted. Okay, so this is homework for you. And also there is another lemma for you. Lemma append length. I think this is a similar lemma that was given to you as a homework in the previous lectures. If you have already proved that lemma, then this should not be difficult for you to prove it. So for any type variable x, L1, L2 of type list x, these are the two lists, and we say that length of the concatenated list L1 and L2 is equal to if their lengths are added and separately. So length of L2. So this is another homework for you. Let me try remove this type of list just like we did here. So if we do not assign a type to type variable x, it is still accepting it, and it is automatically entering the type of type variable x as the type. So it is okay if you sometimes skip the type of variables or the type of arguments, because Coq is quite powerful in many cases that it can infer the type of variables automatically. So fill in here, and this is also admitted, so that it is an exercise or homework for you. So similarly, we can there can be another homework for you. Theorem reverse is involutive. We have already proved this for specific type, so it should not be difficult for all x of some type, and for all L of list x, we can say that reverse applied twice to a list is equal to the same list. And this is again a proof mode, and this is fill in here. Fill in here. So fill in here means that it is the homework for you, and this is again admitted. Okay, so these are the four assignments or homeworks for you. Please complete them. I hope there will be no problem because we have already worked on similar list. They are just defined for specific types, and currently we are working on a more generalized form of list. And remember that these theorems and lemmas are generic for every type of list, so we can apply them to list of any other types.